On the 17th of August 2017, at 12:41 in the afternoon, Universal Time, every gravitational wave detector on Earth went off simultaneously. The LIGO detectors in Hanford, Washington, and Livingston, Louisiana. The Virgo detector in Cassina, Italy. All three instruments recorded a signal that lasted approximately 100 seconds, far longer than the brief chirps from black hole mergers that the detectors had been recording since the first detection in 2015. This was something different, something that the detectors had been designed to find but had never yet seen. And within 2 seconds of the gravitational wave signal ending, a gamma ray burst was detected by the Fermi Gamma Ray Space Telescope arriving from the same direction in the sky. For the first time in the history of astronomy, an event beyond our solar system had been detected simultaneously in gravitational waves and in light. The event was a collision between two neutron stars located approximately 130 million light years away in the galaxy, NGC, 4,993 in the constellation Hydra. Two of the most extreme objects in the universe, each one a sphere roughly 20 kilometers across, containing more mass than our sun, had been spiraling toward each other for hundreds of millions of years and finally merged. The collision lasted less than 2 seconds, and in those 2 seconds, the universe produced more gold than exists in all the stars of our galaxy combined. I want to take you through what happened in those 2 seconds, what the physics was doing, what was produced, and why, of all the extraordinary events that occur in the universe, this one is the most violent, the most productive in terms of the elements it creates, and the most significant for the question of where everything you are made of actually came from. And I want to tell you about a system in our own galaxy, in our own cosmic neighborhood, where the same countdown is running, where two neutron stars are already spiraling toward each other, where the most violent event in the universe is already scheduled, and where the physics says it is overdue. Let me start with what neutron stars actually are, because I think they are underappreciated objects in the popular imagination of the cosmos. Black holes get the attention, but neutron stars are, in their own way, more extraordinary. They are what remains after a star, between roughly 8 and 20 solar masses, exhausts its nuclear fuel and undergoes a core collapse supernova. The outer layers of the star explode outward. The inner core collapses under its own gravity. But unlike a more massive star, whose core collapse produces a black hole, the core of a star in this mass range reaches nuclear density and then stops. Stopped not by any ordinary force, not by thermal pressure or electromagnetic pressure, but by the quantum mechanical pressure of neutrons packed as closely together as the physics of nuclear matter will allow. The resulting object is a neutron star. Its mass is typically between 1.2 and 2.2 times the mass of our Sunday. Its radius is approximately 10 to 12 kilometers, roughly the size of a city. The density is approximately 400 trillion grams per cubic centimeter. A teaspoon of neutron star material would weigh about as much as Mount Everest. The surface gravity is roughly 200 billion times the surface gravity of Earth. If you were somehow standing on the surface of a neutron star, the gravitational force would be so strong that the concept of standing would be meaningless. You would be flattened to a thickness of a few atoms before your consciousness had time to register that you were there. Neutron stars rotate rapidly. Conservation of angular momentum, the same principle that makes a spinning figure skater speed up when she pulls her arms in, accelerates the rotation enormously as the star collapses from a sphere hundreds of thousands of kilometers across to a sphere 10 kilometers across. Some neutron stars rotate hundreds of times per second. These rapidly rotating neutron stars, called millisecond pulsars, are among the most precise clocks in the universe. They emit beams of radio waves from their magnetic poles, and as they rotate, those beams sweep across space like lighthouse beams. When the beam happens to sweep across Earth, radio telescopes detect a regular pulse. The precision of those pulses rivals atomic clocks. Neutron stars rotate rapidly. Conservation of angular momentum, the same principle that makes a spinning figure skater speed up when she pulls her arms in, accelerates the rotation enormously as the star collapses from a sphere hundreds of thousands of kilometers across to a sphere 10 kilometers across. Some neutron stars rotate hundreds of times per second. These rapidly rotating neutron stars, called millisecond pulsars, are among the most precise clocks in the universe. They emit beams of radio waves from their magnetic poles, and as they rotate, those beams sweep across space like lighthouse beams. When the beam happens to sweep across Earth, radio telescopes detect a regular pulse. The precision of those pulses rivals atomic clocks. I want to convey the density of a neutron star in a way that goes beyond the usual comparisons, because the usual comparisons, a teaspoon weighing as much as a mountain, do not fully communicate what nuclear density actually means for the physics inside the object. Inside a neutron star, the distance between adjacent neutrons is approximately the same as the distance between adjacent protons and neutrons inside an atomic nucleus. The entire neutron star is, in a sense, one enormous atomic nucleus. Not a collection of nuclei with electrons filling the space between them, like ordinary matter, but a continuous uniform sea of neutrons packed at nuclear density for 10 to 12 kilometers in every direction. The pressure at the center of a neutron star is incomprehensible. It is roughly 100 trillion times the pressure at the center of the Earth. At those pressures, the physics of dense matter is genuinely uncertain. We do not know with confidence what the equation of state of matter is at neutron star densities. There may be phase transitions from a neutron gas to exotic states of matter like hyperons, where quarks rearrange themselves into strange combinations, or quark-gluon plasma, where individual quarks are no longer confined within nucleons. The interior of a neutron star is one of the most extreme and least understood environments in the universe. The uncertainty about the equation of state is not just an academic question. It directly affects the maximum mass a neutron star can have before it collapses to a black hole. The observations from GW170817 placed constraints on the equation of state by measuring the tidal deformability of the neutron stars during the merger, how much each star was deformed by the gravitational pull of the other. The more deformable a star, the softer the equation of state. The GW170817 data favored a relatively soft equation of state and constrained the neutron star radius to be between roughly 11 and 13 kilometers. This is currently one of the most important constraints we have on the physics of dense matter. Neutron stars also have magnetic fields of extraordinary strength. Typical neutron star magnetic fields are 1 trillion times stronger than Earth's. Magnetars, the most magnetized neutron stars, have fields 1,000 times stronger still. These magnetic fields are responsible for the radio emission that makes pulsars detectable and are involved in the gamma ray emission from magnetar flares, which are among the most energetic events in our galaxy. It is through this precision pulsar timing that the neutron star merger story really begins. In 1974, the astronomers Russell Hulse and Joseph Taylor discovered a pulsar in a binary system. Not a single neutron star, but 2 neutron stars orbiting each other. The system was designated PSR J0737-3039+16, and it was one of the most important astronomical discoveries of the 20th century. Hulse and Taylor won the Nobel Prize in Physics in 1993 for finding it. But the reason it earned a Nobel was not just that it was an interesting binary system. It was what the system was telling them about physics that had never been directly tested before. The 2 neutron stars in PSR B1000 913 plus 16, orbit each other in an ellipse that takes approximately 7.75 hours to complete. They are close, separated by about the diameter of our sun at their closest approach, and they are losing energy. The orbit is slowly shrinking. The two stars are getting closer together with each passing year. The rate at which they are losing energy and spiraling inward was calculated by Hulse and Taylor, and compared to the prediction of general relativity for the energy radiated as gravitational waves by a binary system of precisely this configuration. The agreement was extraordinary. The system was losing energy at exactly the rate that general relativity predicted it would lose through gravitational wave emission. This was the first indirect evidence that gravitational waves exist. Before LIGO detected gravitational waves directly in 2015, Hulse and Taylor's observation of this energy loss was the strongest evidence we had that the universe was genuinely doing what Einstein's equations said it should do. The energy was going somewhere. The orbit was shrinking. And the only thing that could carry that energy away was gravitational waves. PSR B 1913 plus 16 will merge in approximately 300 million years. The two neutron stars will spiral closer and closer together, radiating gravitational waves as they go until they are moving at a significant fraction of the speed of light, and the gravitational wave emission reaches catastrophic levels, and then they will collide. But before I describe what happens at the collision, I want to tell you about another system, one that is further along in its countdown, one that will merge sooner. The system is designated PSR J0737-3039. It was discovered in 2003 and is the only known double pulsar system, a binary in which both neutron stars are active pulsars whose timing can be measured simultaneously. This makes it the most precisely characterized binary neutron star system in existence. We know its orbital parameters with extraordinary precision. We know the masses of both neutron stars to better than a fraction of a percent. And we know the rate at which the orbit is decaying. PSR J0737-3039 is losing orbital energy at a rate consistent with gravitational wave emission and will merge in approximately 85 million years. 85 million years is a long time. It is not overdue in any human sense. But let me put it in perspective. The dinosaurs were wiped out 66 million years ago. The merger of PSR J0737-3039 is 85 million years away. On geological timescales, these are comparable numbers. The merger is a real astronomical event in the finite future of our galaxy, not a remote abstraction. And 85 million years is nothing on the timescales of the universe. The universe is 13.8 billion years old. 85 million years is roughly 0.5% of the current age of the universe. On cosmological timescales, this merger is practically imminent. Moreover, PSR J0737-3039 is about 2,000 light years from Earth. That is close in galactic terms. Eta Carinae, which I discussed in an earlier video, is 7,500 light years away. The double pulsar is within 2,000 light years. When it merges, 85 million years from now, the gravitational waves it produces will pass through the Earth. The gamma ray burst it produces, if its rotation axis is oriented toward us, will reach us. The optical and radio afterglow will be visible. Whether the gamma ray burst is aimed at Earth, we do not know. The orientation of the binary's orbital axis relative to our line of sight is measurable, and the current orientation suggests the burst would probably not be aimed directly at us, but probably is not certainly. And 85 million years is a long time for the orbital precession to shift the geometry. Now let me take you back to the 17th of August, 2017, and the 2 seconds that changed our understanding of where the elements of the universe come from. GW170817, as the event is now designated, was unlike anything the LIGO-Virgo network had seen before. The gravitational wave signal was qualitatively different from the black hole merger signals that had been detected since 2015. Those signals were brief chirps, a fraction of a second long, produced by the final moments before two black holes merged. The GW170817 signal lasted 100 seconds because the two neutron stars were less massive than the black holes in previous detections and therefore spiraled together more slowly. The signal swept upward in frequency as the stars accelerated toward each other, a chirp that began in the audible range of human hearing and swept up to several hundred hertz as the stars made their final approach. If you had somehow been listening to the gravitational wave signal of GW170817, if you could convert the strain in space-time directly to sound pressure in air, you would have heard a tone that rose over the course of about a minute from a low rumble to a high whine and then suddenly cut off as the stars merged. It is one of the most extraordinary sounds in the universe, and no one heard it. Because gravitational waves do not interact with matter in any way that biological organisms can detect. They pass through every human being on Earth, through every atom of the planet, changing the length of every measuring stick by less than 1,000th the diameter of a proton, and we're gone. That is what I mean by silence. Not the absence of physical disturbance. The presence of physical disturbance so subtle that it is completely undetectable without instruments that took decades to develop and billions of dollars to build. The most violent event in the universe passes through us in silence because our physical reality is simply too large, too massive, too inert to respond to the geometry of space-time changing at the level of parts per 10 to the 21. That is what I mean by silence. Not the absence of physical disturbance. The presence of physical disturbance so subtle that it is completely undetectable without instruments that took decades to develop and billions of dollars to build. The most violent event in the universe passes through us in silence because our physical reality is simply too large, too massive, too inert to respond to the geometry of space-time changing at the level of parts per 10 to the 21. Let me give you a sense of how extraordinary the LIGO measurement actually is, because I think it is one of the most remarkable feats of engineering and physics in the history of science. The LIGO detectors are essentially enormous laser interferometers. A laser beam is split and sent down two arms, each 4 kilometers long, then reflected back and recombined. If the two arms are exactly the same length, the light waves recombine perfectly and cancel each other out in the detector. If the lengths differ by even an infinitesimal amount, the recombination is imperfect and the detector sees a signal. When a gravitational wave passes through the detector, it stretches space-time slightly in one direction and compresses it in the perpendicular direction, then switches. This alternating stretch and compression slightly changes the relative lengths of the two arms. The change is what LIGO detects. How large is the change? For the strongest signals LIGO has detected, the change in arm length is approximately 10 to the minus 18 meters. That is 1 attometer, or 1,000 times smaller than a proton. The 4-kilometer arms change length by less than 1,000th of the diameter of a proton. To detect this change, LIGO uses laser beams of extraordinary intensity, sophisticated noise cancellation techniques, seismic isolation, that suspends the mirrors on 4-stage pendulum systems to decouple them from ground vibrations, and signal processing algorithms that extract the gravitational wave signal from a background of noise that would otherwise completely overwhelm it. The fact that this works, that we can detect changes in length of less than a proton diameter using a machine that sits on the surface of the Earth and is subject to all the vibrations and noise of the terrestrial environment, is a technological achievement that I find genuinely awe-inspiring. It required decades of development, multiple generations of detector improvements, and the work of thousands of scientists and engineers. And that instrument detected the gravitational waves from GW073817 while the event was occurring 130 million light years away. While two neutron stars were spiraling together at a fraction of the speed of light, synthesizing gold in conditions of nuclear density and billion-degree temperature, LIGO was sitting in Louisiana, measuring the distortion of space-time at the level of parts per 10 to the 21, extracting the signal from the noise, and sending an alert to telescopes around the world within minutes. The gamma-ray burst that followed the gravitational wave signal by 2 seconds told us where in the sky to look. Within 11 hours, optical telescopes had identified a new source of light in the galaxy, NGC 4993, a faint blue point that had not been there before. Over the following days, the color of that light changed from blue to red. The spectrum revealed the presence of specific heavy elements. Strontium was confirmed almost immediately, and subsequent analysis has identified signatures of a wide range of heavy elements, including gold, platinum, cesium, tellurium, and many others. The reason these elements were present in the light from GW070817 is the R process, the rapid neutron capture process, which I mentioned in the video about the atoms in your body, but which I want to explain in more detail here because it is central to the story of neutron star mergers. In the R process, atomic nuclei are bombarded with neutrons so rapidly that they cannot decay before the next neutron arrives. Each neutron capture adds mass to the nucleus. The nucleus becomes heavier and heavier, incorporating more and more neutrons, becoming increasingly neutron-rich and increasingly unstable. When the neutron flux eventually subsides, the unstable neutron-rich nuclei begin to decay, each decay process releasing energy and transforming the nucleus toward a more stable configuration. The cascade of decays produces a wide range of heavy elements, specifically the elements with atomic numbers above roughly 50, above the iron and nickel that are the heaviest elements that stellar fusion can produce efficiently. For decades, astrophysicists knew that the R process was responsible for producing these heavy elements, but they did not know where in the universe it occurred. Two sites were proposed: supernovae, where the core collapse creates a flood of neutrons, and neutron star mergers, where the collision of two neutron stars liberates enormous amounts of neutron-rich material. Both sites could, in principle, support the R process. Which one actually dominated the production of R process elements in the universe was a major open question. For decades, astrophysicists knew that the R process was responsible for producing these heavy elements, but they did not know where in the universe it occurred. Two sites were proposed: supernovae, where the core collapse creates a flood of neutrons, and neutron star mergers, where the collision of two neutron stars liberates enormous amounts of neutron-rich material. Both sites could, in principle, support the R process. Which one actually dominated the production of R process elements in the universe was a major open question. Let me tell you more about the R process itself, because I think its physics deserves more attention than it usually gets in popular accounts of neutron star mergers. The periodic table, as you learned in school, is organized by atomic number, the number of protons in the nucleus. Hydrogen has 1 proton, carbon has 6, iron has 26. Gold has 79, uranium has 92. The heavier an element, the more protons in its nucleus. Getting protons into a nucleus requires overcoming the electromagnetic repulsion between them. Protons are positively charged, and positive charges repel each other. At the distances relevant to nuclear physics, this repulsion is enormous. The only force that can overcome it and bind protons together in a nucleus is the strong nuclear force, which operates at even shorter ranges and is much stronger than electromagnetism at those distances. But building heavy nuclei by adding protons one at a time is energetically expensive, which is why stellar fusion stops at iron. Adding protons to iron requires more energy than it releases. Adding neutrons is different. Neutrons carry no charge. There is no electromagnetic repulsion to overcome when you add a neutron to a nucleus. The strong nuclear force simply grabs the neutron and holds it. So building heavy nuclei from neutron-rich environments is energetically feasible in a way that building them by proton addition is not. This is the fundamental reason why the R process, which operates in neutron-rich environments, can build nuclei up to and beyond uranium. In the R process, the neutron flux is so intense that a nucleus can capture 10, 20, 30 neutrons in rapid succession before it has time to decay. This creates highly neutron-rich, unstable nuclei well off the valley of stability in the nuclear chart. These nuclei cannot exist in ordinary laboratory conditions. They would beta decay almost instantly, a neutron converting to a proton and emitting an electron and an antineutrino. But in the R process environment, the neutron capture rate is faster than the beta decay rate, so the nuclei keep accumulating neutrons. When the neutron flux eventually drops, as the material expands and cools after the merger, the neutron-rich nuclei begin to decay. Each beta decay converts a neutron to a proton, moving the nucleus toward the valley of stability. The cascade of decays, proceeding through a sequence of unstable nuclei, eventually produces the stable heavy elements we observe. Gold, with its 79 protons, sits in a region of the nuclear chart that is specifically populated by the R process decay cascade. It is, in a precise nuclear physics sense, a daughter product of the neutron-rich nuclei synthesized in the most violent moments of the merger. The temperature required for the R process is hundreds of billions of degrees. The neutron density required is something like 10 to the 24th neutrons per cubic centimeter. No environment on Earth, not even nuclear weapons, can approach these conditions. The R process is exclusively a phenomenon of the most extreme astrophysical events. And neutron star mergers are currently our best characterized site where those conditions are achieved. GW070817 answered it. The spectroscopic signatures of heavy R process elements in the light from the merger confirm that neutron star mergers are sites of R process nucleosynthesis. And the amount of material produced, estimated from the brightness and color of the optical transient over the following days, was staggering. The merger of GW070817 produced approximately 1/10 of a solar mass of R process elements. That includes roughly 10 Earth masses of gold and platinum each, along with comparable amounts of uranium, thorium, and the other heavy elements. 10 Earth masses of gold. In a single collision lasting less than 2 seconds, 10 Earth masses of gold. In a single collision lasting less than 2 seconds. I want to stay with the significance of GW070817 for a moment beyond the gold, because the event was important for reasons that go beyond nucleosynthesis. It was the first event that allowed what astronomers call multi-messenger astronomy, the simultaneous observation of an astrophysical event through multiple different physical channels: gravitational waves, gamma rays, X-rays, optical light, and radio waves, each carrying complementary information about the physics of the event. The 2-second delay between the gravitational wave signal and the gamma ray burst was itself an extraordinarily important measurement. It told us that gravitational waves travel at the speed of light, not faster, not slower. This was a direct test of general relativity that ruled out large classes of alternative theories of gravity that predicted gravitational waves might travel at a different speed than electromagnetic waves. The agreement was extraordinary. The speeds were equal to within a part in 10 to the 15th. General relativity passed yet another test with flying colors. The event also produced an independent measurement of the Hubble constant, the rate at which the universe is expanding. The gravitational wave signal from the merger, combined with the distance inferred from the signal's amplitude and the redshift of the host galaxy measured optically, gave a measurement of the Hubble constant that was independent of both the cosmic microwave background method and the distance ladder method. The value came out at approximately 70 kilometers per second per megaparsec, right between the two discrepant values that define the Hubble tension. It was not precise enough to resolve the tension, but it established the method. Future neutron star mergers detected by gravitational wave observatories will provide additional measurements, and as the statistics accumulate, gravitational wave cosmology may eventually resolve the Hubble tension by providing a completely independent determination of the expansion rate. GW170817 was also important for what it told us about neutron star interiors. The tidal deformability, how much the neutron stars were distorted by each other's gravity during the inspiral, was measurable from the gravitational wave signal. This placed direct constraints on the equation of state of dense nuclear matter, constraints that could not be obtained from any laboratory experiment or any other astronomical observation. The measurement ruled out equations of state that would make neutron stars very large and puffy, favoring a more compact configuration consistent with radii of 11 to 13 kilometers. The physics of matter at nuclear density, which is relevant to understanding heavy ion collisions and the behavior of atomic nuclei themselves, was constrained by an observation of two stars colliding 130 million light years away. Every gold atom on Earth, in every gold ring, every gold coin, every circuit board, every electrical connector, every gold bar, in every vault, in every central bank, was produced in an event like GW170817. Not necessarily that specific event, which was 130 million light years away and whose gold is dispersed through that galaxy, but an event of the same type, a neutron star merger that occurred somewhere in the Milky Way, or in a galaxy whose material was later incorporated into our galaxy billions of years ago. The gold that was eventually incorporated into the solar system arrived there as the dispersed debris of ancient neutron star collisions, seeding the molecular cloud that formed the sun, becoming part of the Earth, eventually being mined and shaped and worn. When you look at something made of gold, you are looking at the preserved residue of the most violent event in the universe. The atoms in that gold were synthesized in 2 seconds of neutron star collision, dispersed into space, drifted for billions of years, and eventually found their way into the planet you live on. I find this extraordinary in a way that is different from any other aspect of stellar nucleosynthesis. The carbon in your body, the oxygen you breathe, the iron in your blood, those were all produced in stellar cores and dispersed in supernovae, processes that are dramatic but that unfold over millions of years and that are in some sense the ordinary life cycle of stars. The gold and the platinum and the uranium and the other heavy R process elements were produced in an event that lasted less than 2 seconds. In 2 seconds, an event generated more gold than exists in all the stars of the Milky Way combined. And then those atoms scattered into space and waited for billions of years to become part of something. Now, let me take you deeper into what actually happened during those 2 seconds, because the physics is extraordinary, and I want you to have a sense of what the collision actually involved. In the final moments before the merger, the two neutron stars were orbiting each other at a significant fraction of the speed of light. At the point of last stable orbit, they were separated by roughly 30 kilometers, just twice their combined radii, orbiting at roughly 1,000 times per second. The gravitational wave emission at this point was catastrophic. The power output in gravitational waves was approximately 10 to the 47 watts, roughly equal to the total luminosity of the observable universe in all forms of electromagnetic radiation combined, The universe was radiating as much energy and gravitational waves from this single collision as it was radiating in all the light from all the stars and all the 2 trillion galaxies simultaneously. And this lasted for a fraction of a second before the stars touched. When they touched, the collision was not like 2 balls slamming together. It was more like 2 extremely dense fluids merging at relativistic speeds. The neutron stars deformed each other gravitationally before contact, each one raising enormous tidal bulges on the other, distorting from spheres into ellipsoids. When they finally made contact, the outer layers of the stars splashed outward in a spray of neutron-rich material, some of it ejected with enough velocity to escape the system entirely, some of it falling back to form an accretion disk around the remnant. The remnant itself is uncertain. It might have collapsed immediately to a black hole. It might have formed a hypermassive neutron star, spinning so rapidly and supported by its rotation against further collapse that it survived for milliseconds or seconds before finally collapsing to a black hole. The gravitational wave data from GW073817 do not clearly distinguish these possibilities because the post-merger signal, if there was one, was below the sensitivity threshold of the detectors. What we do know is that within seconds to minutes, a structured jet of material was launched along the rotation axis of the system at a velocity very close to the speed of light. This jet produced the gamma ray burst detected by the Fermi telescope. The jet punched through the slower moving material surrounding the merger site, expanding as it traveled, eventually producing the afterglow in X-rays, optical, and radio that was observed over the following weeks and months. And in the material ejected from the merger, at temperatures of hundreds of billions of degrees, in conditions of neutron density that no other astrophysical environment can replicate, the R process ran. Nuclei were built up from neutrons at rates so fast that the neutrons could not decay before the next capture. In seconds, the full range of heavy elements was synthesized. In hours, the temperature dropped enough for atoms to form. In days, the expanding cloud of newly synthesized material was glowing at optical wavelengths as the unstable nuclei decayed, and the light it emitted carried the spectroscopic signatures of gold and platinum and strontium and all the other elements that the R process produces. The light took 130 million years to reach us. The gold it revealed had been traveling through space for 130 million years. When we saw that light in 2017, we were seeing the aftermath of an event that occurred before the first primates existed on Earth, before the dinosaurs went extinct, before the first flowering plants appeared. The universe had been carrying that gold for longer than complex land life has existed on this planet. Now, let me connect all of this to the question that I raised at the beginning and that I want to bring home before we close. The question of the event that is overdue near us. I want to be precise about what overdue means in this context because I use the word deliberately and I want to justify it. In the context of PSR J0737-3039, overdue does not mean that the merger was predicted to have already happened and has not occurred. It means something more specific and more interesting. It means that based on the statistics of the known population of binary neutron star systems in the Milky Way and on the estimated merger rates derived from those systems, we would expect to have detected a neutron star merger in our galaxy or its immediate neighbors within the observational lifetime of modern astronomy. We have not. The estimated rate of neutron star mergers in a galaxy like the Milky Way is approximately 1 per 10,000 to 1 per 100,000 years, depending on the model. Over the 60 years or so that we have had instruments capable of detecting the aftermath of such an event, the probability of one occurring is small but not negligible. The absence of a detected merger in our galaxy in the modern era is not alarming. It is consistent with the statistics. But here is what is more interesting. The estimated rate of mergers in the volume of space accessible to our current gravitational wave detectors, roughly 1 billion cubic light years, is roughly 1 per year. And LIGO has been running at increasing sensitivity for the past decade. The detections have been coming in at roughly the expected rate. The statistics are consistent. What is interesting is the distance distribution. The mergers we have detected are all at cosmological distances, tens to hundreds of millions of light years. None has occurred in our own galaxy or its immediate companions. This is entirely consistent with the statistics. Our galaxy is one among many, and the probability of any given merger occurring in our specific galaxy in any given decade is small. But it will eventually happen. The binary neutron star systems in the Milky Way, including PSR J0737-3039, are on a countdown. The merger is coming. And when it comes, it will be by far the closest and most observable neutron star merger in recorded history. How close could a neutron star merger be and still be safe? The gamma-ray burst from GW170817, which was aimed away from Earth at an angle of roughly 30 degrees from our line of sight, was already faint by the time it reached us. If a similar merger occurred in the Milky Way, say 10,000 light years away, and if the jet were aimed at Earth, the gamma-ray fluence would be orders of magnitude larger than from GW170817. At 10,000 light years, a strongly beamed gamma-ray burst could deposit enough energy in Earth's atmosphere to seriously deplete the ozone layer. The effects would be comparable to or worse than the Eta Carinae scenario I described in the previous video. But the probability of being in the beam is small, as I discussed in that video. The jet opening angle is a few degrees. The probability that Earth is in the beam of a randomly oriented merger in the Milky Way is roughly 1%. And the probability that the nearest merger to us is also aimed at us is smaller still. The more likely scenario is that a future Milky Way neutron star merger will be spectacular but not threatening. A gravitational wave signal lasting over a minute, far longer than anything LIGO has detected, strong enough to be measured with high signal-to-noise by every gravitational wave detector on Earth and in space. A gamma-ray burst visible in the sky as a brief flash, comparable in brightness to the Moon, even if Earth is not in the direct beam. An optical transient visible to the naked eye for days, the kilonova, glowing in the specific colors of gold and platinum and other heavy elements being synthesized in real time. A spectacle that no human civilization has ever witnessed, because no neutron star merger has occurred close enough to be visible to the naked eye in all of recorded history. And in the wave of gravitational signal from that event, and in the light from that event, and in the material that the event sends into the interstellar medium of our galaxy, we will see and measure the most direct evidence ever obtained of where the heavy elements in the universe come from. We will watch, in real time, a kilonova synthesizing gold and platinum and uranium in the conditions that no laboratory on Earth can replicate. We will see the R process operating, not as a theoretical prediction or an inference from ancient stellar spectra, but as a direct observation of an event occurring in our own galaxy. I think about this sometimes when I look at the night sky. Somewhere out there, among the 100 billion stars of the Milky Way, 2 neutron stars are spiraling toward each other right now. They have been spiraling for millions or billions of years. They have millions or billions more years to go. But they are on the countdown. The orbit is shrinking. The gravitational waves are carrying the energy away. The merger is inevitable. And when it happens, the most violent 2 seconds in the history of our galaxy, since the last such event will occur, in complete gravitational silence as far as the biological world is concerned, but in a blaze of light and heavy elements that will reach every corner of the Milky Way. The gold in your wedding ring, if you have one, or in the electronic components of the device you are reading this on, arrived here from an event just like that one. From 2 seconds of cosmic violence that occurred billions of years ago, somewhere in or near our galaxy, that produced in those 2 seconds more gold than the sun will ever produce in its entire lifetime. Those atoms traveled through space for billions of years, mixed into the gas and dust of the interstellar medium, condensed into the solar nebula, became part of the Earth, were eventually concentrated by geological processes into veins in rock, were mined, refined, and fashioned into something you carry with you now. I want to push the implications of this one step further, because I think there is something important in the specific history of gold that is not usually told even in the best accounts of nucleosynthesis. The neutron star merger that produced the gold in our solar system did not occur in our galaxy, or at least it may not have. The chemical evolution of galaxies is a complex process, and the heavy elements in any given star system represent a mixture of contributions from many different generations of stellar evolution in many different environments. Some of the gold on Earth may have originated in mergers that occurred in dwarf galaxies that were subsequently incorporated into the Milky Way through galactic mergers. Some may have occurred in the early Milky Way itself. Some may have been contributed by the predecessor stars that formed before the Milky Way's current disk structure was established. The gold did not come from a single event. It came from many events distributed across the history of the galaxy and its predecessors, each event synthesizing heavy elements that were eventually mixed into the interstellar medium and redistributed by the dynamics of galactic evolution. The specific gold atoms in any given object on Earth have specific origins in specific neutron star mergers, but those mergers may have occurred at vastly different times and places, ranging from events in the first billion years of galactic history to more recent events in the past few billion years. What we know from GW070817 is that the process is ongoing. Neutron star mergers are still occurring. New gold is being synthesized in mergers happening right now in our galaxy and in galaxies throughout the observable universe. The gold that future stars and planets and civilizations will be made of is being manufactured in events that are occurring this moment as you read this, and whose light will not reach us for millions or billions of years. The universe is not a static inventory of fixed material. It is an ongoing process of element synthesis, continuously producing new copies of every element in the periodic table, including gold, in the most violent events it can generate. The gold on Earth is old gold, synthesized billions of years ago. But new gold is being made right now in the neutron star mergers occurring throughout the universe, waiting to be incorporated into future planetary systems and future life. The universe is not quiet about how it makes things. It is just that the silence in which it works is not the absence of violence. It is the violence of space-time itself distorted at levels too subtle for our bodies to feel, passing through us and through the planet and through everything, recorded only by the most sensitive instruments our civilization has ever built. The most violent event in the universe happens in silence, not because it is gentle, but because the medium through which it speaks is space-time rather than air, and space-time whispers at a frequency that biology cannot hear, but physics can. And now, so can you. If this changed how you think about the gold in your life, about where the heaviest elements in your world actually came from, tell me in the comments. Tell me whether you knew that neutron star mergers were the primary source of gold in the universe, and if so, when you learned it, and what it did to the way you thought about those objects. These are the conversations that matter. And subscribe if you want more of this, the real physics of where things come from, and what the universe is doing while we are not looking